Good afternoon, everyone. Hope you have enjoyed the workshop so far and enough time for a quick lunch. I'm Xu from NTU, and I'm the co-director of SGEC. It's my great pleasure to chair this afternoon session. So welcome to session 4, SGEC projects presentation. These are some of the projects, including the previous one, the biopolymer by Prof. Ali, which were awarded over the last 2 to 3 years since the establishment of SGEC. We are excited to listen to the findings of these projects. Our first speaker today is Professor Grzegorz Lisak, who is from School of Civil and Environmental Engineering, NTU. He's the Director of Residues and the Resource Reclamation Center, Nanyang Environment and Water Research Institute, NURI. His title of presentation is Carbon Capture Through Innovative Waste Valorisation and Integrated Resource Management. Professor Lisak, please.
Good afternoon, everyone. Thank you, Professor Shurong, for the introduction. Let me share the slides. Let me say again, welcome everyone to my presentation. First of all, I would like to thank the Singapore Energy Center for awarding us the grant that allows us to investigate some of the very interesting concepts around using waste materials and their possibility for capturing CO2 that ultimately could serve the purpose of linking waste and recovery of resources from waste. Let me check if can I have the next slide, please? So before I do that, I would like to introduce people who also stand behind that work. So co-investigators in this project is Paul Yu Ven, Dr. Andrei Veksha, Dr. Chan Wei Ping, also Mr. Preston Tan. Can I go to the next slide, please? So let's have a look here at what our proposal and project is about. So let's imagine that we have that CO2 capture capabilities. You can see that plant that we envisage in the middle of the slide. And that process that we wish to look at is actually based on some called chemical looping system that would allow us to tap on waste materials in Singapore, put them in a loop and subsequently capture CO2 and release CO2. Okay, so again, to reinforce, the source of CO2 would come from waste to energy plants as well as CCGT power plants. And we would use a sorbent type of materials derived from incineration ashes as well as gasification ashes. These materials would pre-concentrate the CO2. So at the end of the process, we would capture relatively high concentration of CO2 stream, which would have very little contaminants and could serve the purpose of generating chemicals and fuels. And naturally, in this process, we would hope to have a high percentage of removal of CO2 from the flue gas. So then the flue gas actually entering the atmosphere would be considered decarbonized. Alongside this process, we would also look at energy recovery. Since the high temperature CO2 capture process would also generate a lot of energy, heat, we would tap on it to further get electricity out of this process. The sorbent that is used for the CO2 capture would actually be reused after the life served for the purpose of CO2 capture would come. And where those could be applied? Naturally, people investigate how ashes could serve the purpose of as a construction materials to replace sand, to replace aggregates, depending on their size. And this is exactly what we wish to look at in this project. And ultimately, we are interested in serving the safe, environmentally safe materials for the construction industry. We realized that, of course, further reprocessing of ash would most probably be required as we deal with sometimes hazardous nature of, for example, fly ash coming from waste to energy plants. Additionally, in Singapore, we do have desalination plants. What it means in practice is that except of water recovered, we get a lot of residue, which is brine. That brine currently is simply disposed into the sea. And we wish to tap on that resource because it's totally unaddressed. And we wish to see if we can further recover some of the carbon out of brine. So utilize the brine to recover carbonates. Can I have the next slide, please? So again, here you have that map, which I just presented in a last slide. So ultimately, we are looking at how to put everything together to serve the purpose of a more sustainable Singapore and possibly expand that utilization of the technology at other geographies. So the process that we are dealing with has a great promise because it is scalable. If you look at the material available in Singapore, we are talking about having a possible sorbent type of material of about 600,000 tons per year of incineration bottom ash and 120,000 tons per year of incineration fly ash. Currently, generation of gasification fly ash is very limited because we are still yet only at the demonstration plant operated by NTU. But we hope in the future that would change and new type of waste to energy plant in Singapore with a more advanced recovery of materials and energy would become reality. Additionally, what we have in Singapore is 143 million cubic meters of brine per year. So what does it mean in terms of CO2 capture? When we consider ash, we can envisage of about 400,000 tons per year of CO2 displacement by ash-derived cement. Also, when we talk about the brine, we can look into 288,000 tons per year of CO2 sequestration. So except of being scalable, the material is already there. So now the whole idea is to link them both together for a possibility of optimization and maximization of CO2 capture capabilities and recovery of materials. So cost effectiveness is something that we look into. And yet again, this process that we are developing has that promise of being cost effective. I understand they've been questioning about what could be the CO2 tax. We did use here a possibility of avoidance of about 17 Sing dollars per ton of CO2. We understand that is not the finalized how this tax could look like, but we all know that it is progressive for what we have now. Then we talk about the waste and we talk about avoidance of landfilling the waste and converting them into useful construction type of materials. And that comes at the cost of about 77 Sing dollars per ton. So it's ultimately when we calculate all the resources available and possibility of savings for CO2 release as well as the landfilling and subsequently use it as a construction material, the numbers speak for themselves. Of course, we link that to the performance of the material. So alongside the cost effectiveness, we can identify that, for example, brine can capture we can recover carbon in form of carbonates of about 1 gram per liter of brine. Then when we talk about the ash, some of the ashes that we work on have the capability of capture CO2 of about 400 milligrams per gram of sorbent. And this is yet something that we still wish to work on. We identify different type of ashes that are available in Singapore. There is difference in the ash composition, and for that reason, their capability of capturing CO2 is also different. The 400 milligrams per gram comes actually from a gasification type of ash that has a high content of calcium oxide that is vital for that CO2 capture capabilities. Next slide, please. So let's come to the heart of the invention that we are working on. I did mention we are working on a chemical looping process. What it means, you can see here in that animation a set of two reactors. One, which is called carbonator, and that one operates at 650 Celsius degree. And the second one is the calciner, which operates at 900 Celsius degree. The sorbent material for us, it would be ash, would be circulated between those two reactors. One reactor, carbonator, is responsible for capturing CO2. So we would intersect that material with the flue gas that contains CO2. Then, once the capture is performed in a fluidized bed reactor, we can start to recovering that CO2 as a concentrated stream of gas. So how to do this is to transfer the sorbent from carbonator to the calciner, and at higher temperature, release the CO2. And that released CO2, again, will be at high concentration, relatively pure. Which could be utilized, for example, for chemical synthesis or a number of different industrial processes, or even food-related applications, if, for example, would be found clean enough or after further purification. So out of the carbonator, the flue gas that exit into the stack would be relatively clean, hopefully with totally not having CO2 in its content. While from the calciner, high concentrated CO2, near 100%. Ultimately, that sorbent material, we know that after a while, may undergo sintering and further decrease in the size. So we understand that it would become considered as a spent material because it would not have that capabilities to capture CO2 any longer. And for the spent material, we are working on developing what to do next. Of course, as mentioned, we wish to apply it as a construction material. So here on the right-hand side, you can see that lab-based equipment that we perform our work on in this SGC project, where we can simulate that looping system and investigate the material in cycles, how many cycles they can perform, what is the capacity, what is the behavior of the material, what is the degree that the material disintegrates or sinters, and so on. You can see that fly ash capture capabilities for CO2 at the bottom of the slide. So the process itself is relatively short. It allows us to investigate the material in terms of fluidized bed reactors in that chemical looping system. Next slide, please. Of course, this sort of carbonation of ash could be realized also through one-off time carbonation, although we see more benefits of implementing chemical looping system. For one-off carbonation, it would mean that we perform that carbonation only once, and we identified that washing the ash is relatively a good solution to increase the capability for the ash to capture CO2, and at the same time to release the chlorides, which are very unwelcome when considering material with the application in the construction. So for that one-time carbonation, we are confident to say that we can reach of about 100 milligrams of CO2 capture per gram of sorbent. Next slide, please. So here is the bunch of tests that we do with that material that we consider as spent. From L1 to L3, those are the methods that would assess the environmental performance of the sorbent or spent sorbent as it is, and also after utilization in the construction materials. So currently we understand we are off what would be required for that material to be used in a safe manner. So further processing or performing a stabilization of some of the impurities if the material could be necessary. For the construction materials investigation, we look at the mortar as well as the concrete itself and such properties as workability and the strength to identify which of these materials are suitable as a replacement for the sand and the aggregates. Next slide, please. I did mention that we are tapping also on brine. And here is what we do with the brine. We can additionally recover carbonates from brine. Taken, we increase the alkalinity of the brine. And to do that, we can intersect the brine together with the ashes. Ashes are highly alkaline. So ultimately, that solution of brine then changes the pH to more alkaline, and we can perform mineralization of CO2 in that high pH. Unfortunately, I'm not able to play a video for you, but what is important to mention is that this carbonation mineralization process of brine is very fast. We can recover 1 gram of carbonates per liter of brine. Here is the product of that mineralization of CO2. And you can see from XRD as well as FDR analysis that the purity is very good. And as compared to a pure commercially available calcium carbonate, there is no much difference in the spectrum. That gives us a promise that this calcium carbonate could be applied in a number of different applications of industrial grade applications, for example, in paper making. Next slide, please. So this is where what we wish to achieve with this project and where we are with the project. So currently we are at the lab scale system through the funding of SGC. The next step is already undertaken. We submitted our proposal to LCER project, and the PI of that project is Assistant Prof. Paul Van New. This project is planned also to be executed together with A-STAR, with Dr. Boudier. And we hope that we will be awarded that project. And if we do, we will be able to take this, this system out of the lab and take it to our facility, our waste to energy research facility that generates actual flue gas. If that is found feasible, together with our industrial partners, we will look at possible industrial collaborations and further upscaling towards the full scale. Next slide, please. So in brief, this is the facility I did mention to you. You have that top view at the bottom of the slide, as well as the cross section. This is a first of its kind in Singapore facility that treats municipal solid waste. So it behaves as a waste to energy plant. It is more advanced than incineration. Instead of ashes, it generates the slag, but it does also generate a fly ash, a small fraction of fly ash that I did mention. We see a great promise of utilizing it as a CO2 capture sorbent. Nonetheless, the facility treats actual waste, which means that the flue gas at the end of the process is very typical to what we have in every waste to energy plant in Singapore. That gives us advantage of testing our capabilities in chemical looping capture and release to tap on very industrial flue gas. And hopefully that project will come to fruition and we will be able to test our technology there. Next slide, please. This is how the facility looks like in real. I do welcome all of you to visit us at some point when that is possible. So we can show you around of what we are doing except of CO2 capture in that waste to energy plant. Thank you for your attention, and I welcome some of the questions.
Thank you, Professor Lisak, for your nice talk. Because of the time, for the interest of time, because we are 5 minutes running behind the schedule, we will not take questions at this moment. I do notice this question in the chat box. Perhaps I will encourage you to reach out to Professor Lisak after the workshop. Thank you, Professor Lisak.